Today we study X21Q. What is a wave? This is an English version. You can download this PDF file from the website kpop.org, and you will find table of contents, X series that is for the General Physics 1, and Y series is for General Physics 2, and there are various subjects related to physics. And in the X series, you will find X21, what is a wave, and X represents the main textbook, and there are Korean and English lectures available on YouTube. 자, 이번 시간에는 웨이브에 대해서 공부해 보기로 합시다. Okay. And then this one also contains checkpoints that are various problems asking you to find a false statement, but however, I believe every statement in this list is true. The lectures for solving these questions are given in Korean and English, and they are also found on YouTube. And then we are now working on a few more questions that represent the derivation in detail. And if I'm not familiar with those questions, then you can refer to NQ just before I take the problem on Q. So, and the Korean version of this lecture for X21QK is available. And after recording this English version, it will be uploaded to our YouTube site. And the YouTube site is youtube.com/KPOPE. And you will find the various playlists. But it's too busy, so I recommend you visit kpop.org and look for what you want. So there are many that every lecture gives the PDF files and you can refer to freely. Okay, let's begin with the X21Q. What is a wave? We consider a time-dependent field. A field is a function of a position, and this is a one-dimensional case. In three-dimensional case, the field is a function of a position vector in general. To simplify our analysis, we first consider the one-dimensional case, and if it is depending also on time, we say it is a time-dependent field. Explain how to compute the derivatives with respect to t or x. This one shows that a function is a multivariable function that involves many variables. In that case, the derivative with respect to a single variable is called partial derivative. Partial derivative, and we do not use df over dt. This is used for this Leibniz operator for the derivative is for a single variable function. Instead, if we have many variables and I would like to vary time only and keeping x as a constant, then we use this operator. So, for example, the partial time derivative of f of t and x is the usual derivative with respect to time. We have shifted time by h and find the difference of the function and divide it by the difference of the argument. We notice that the x is not changing, so x is fixed to be a constant. So we use the partial derivative of f with respect to time. In a similar manner, we can define the partial derivative of f with respect to x, in which we vary x only. Okay, so why don't we compute the second order derivatives? In most textbooks, they say you can repeat the operation of derivative once, twice, triple times, and so on. Why don't we investigate the definition of the second order derivative in more detail? We apply this one to find that the second order derivative is the derivative of the first order. We remember that this is the first order derivative evaluated at t comma x. By the way, what we want to do is to compute the second order derivative. So I'd like to find the difference of the first order derivative by shifting x by h. We find the same thing except that t has been shifted by plus h. This is a time derivative. So time derivative. So at f of t plus h minus f of t, and then it is plus h. So we have t plus 2h subtracted by t plus h. So this is the change in the first order time derivative when I shift time by plus h. We can combine these two fractional rational function to find that we have f evaluated at t plus 2h, and these two are identical terms. So it is doubled to find that 2 minus 2 f of t plus h, and then finally minus minus will give a positive sign on the f of t. This is a way to evaluate the second order derivative by definition. In a similar manner, we can compute the second order derivative of f with respect to x. So this partial derivative can also be obtained in a similar manner, keeping the time the same. We consider the vibration of a string, and the string has the length L, and mass of the string is capital M. We assume that the density of this string is uniform, so the density is mass divided by length, so this is uniform. So if I choose a very tiny piece of this string of length small h that approaches 0, we keep this one to be positive, but the length approaches 0. This infinitesimal amount centered at position x, so it is represented by this interval. Then the mass small m for this tiny piece, because the density is uniform, I can obtain this mass by multiplying the width h by this uniform density. We apply Newton's second law to find out the equation of motion of this vibrating string. The net force applied to the small mass, small m, is, according to Newton's second law, the mass multiplied by the acceleration. The acceleration is the double time derivative of the displacement. The displacement that is measured from the equilibrium position on the horizontal line is called psi t comma x. This shows a distribution, a deviation from the equilibrium point. Okay. And we keep the point x the same because we are interested in the motion of this tiny piece of the string. Because the mass of the string, mass of the string segment of width h is this, we can substitute rho h for the mass m. We know this displacement is a function of time and position, and we fix the position of this segment. So this double time derivative is nothing but the partial time derivative, the second order partial time derivative of this displacement with respect to time. Next we find what this net force applied to the tiny piece of the vibrating string. This one can be measured by estimating the angle of the slope represented by this displacement at time t and at position x. Okay, we have a point x and we have a small interval, tiny interval from centered at x, and its width is h. We find a slope of this curve in the limit as h goes to 0 plus, then it can be approximated as a straight line, and we construct a right triangle. The height represents the change in the position by shifting the x by h. And this amount of change represents this function evaluated at x plus 1/2 of h, subtracted by the function evaluated at x minus 1/2 of h. So slope, this is the theta. Tangent should be the ratio of this difference of this function divided by the finite width. We take the limit as h goes to 0, then it is a certain value. It approaches a certain value. All right, so the force applied to this tiny piece consists of two contributions. The first contribution comes from the tension applied to the right end of this segment. The second force is applied to the opposite direction, approximately opposite direction, downward if the slope is in such a manner. We find that the horizontal contribution and the vertical contribution applies to the variation of this motion of this mass segment. We remember this guy is moving up and down instead of right and the horizontal. If the motion is fixed to this region only, in that case, the horizontal forces is assumed to be cancelled exactly, and the only net force applied to this segment is along the vertical direction. That is true in the limit as theta goes to 0. We remember the tension is this, and that tension is assumed to be constant. What is the vertical component of this tension? That is tangent, evaluated at this point. And what is the vertical contribution to the net force on the left end? That is the same except that we have a negative sign on it. We see the applied direction is downward if the slope is going up as we go to the right. Therefore, this is the net force along the vertical direction, and the horizontal direction, they cancel almost exactly because the horizontal direction is assumed the tau tau, they cancel. Okay? In the limit as the theta goes to 0, tangent theta is nothing but sine theta cosine theta, and this cosine theta approaches 1. Therefore, we can make a good approximation that tangent theta is similar to sine theta. Anyway, the evaluation of tangent theta at x plus 1 half of h and at x minus 1 half of h can be made by using this formula. How? This one is used for the value at the center. Therefore, what we have to do is we apply this function above. We replace this x with x plus 1 half of h. And then we subtract the value by the same thing evaluated on the left hand. That is at x minus 1 half of h. This substitution results in the value that we are very familiar with. Second derivative with respect to, in here, x. Okay, so we substitute these values and make a subtraction and simplify these results altogether. We find the denominator h, but we divide this one by h one more time and multiply. As a result, the numerator denominator shows this approaches the second order x derivative. And then we have over a factor tangent multiplied by that infinitesimal width. We return to this point. Net force is according to Newton's second law, rho h multiplied the second order time derivative. Rho h second order time derivative here. And tau h second order position derivative. Okay. We cancel this common with h and divide both sides by tau. And we have reached the expression that is identical to the general wave equation propagating along the x-axis. We can identify the speed of propagation v by square root of tau over rho. Okay. Consider a wave amplitude multiplied with sinusoidal function whose argument is kx minus omega t. discuss the relationship among the parameters of this wave. Okay, this is a periodic. The spatial component kx returns to the same value of a psi if I substitute the wavelength. So from this, the wavelength is 2 pi over k. We call this k is 2 pi over lambda is a wave number. According to this time-dependent part, we know that this is propagating to the right-hand side. And this variable x identifies the direction of propagation, E1 hat, and according to this negative sign, we have direction of propagation. So if we combine these two, we can construct a wave vector whose magnitude is a wave number and whose direction is the direction of propagation. The minimal time difference to return to the same value of the wave is called the period t, and in a similar manner, we can find the value of capital T expressed in terms of the frequency omega. Again, omega should be expressed in terms of 2 pi over period. We have found that the velocity of this wave is a ratio of the wavelength divided by the period. Using these notations, I can divide this one by 2 pi and multiply it by 2 pi, and this one are represented by the wave number and angular frequency. So ratio of the angular frequency and the wave number is the speed of propagation. We use these, flip the numerator and denominator. Okay, and we multiply lambda both sides, so they cancel to find a period. So we can manipulate these identities to find the various relations among the parameters of this wave. Next, we find the general solution for the wave equation of the string. Now we have additional condition that endpoints of the string are fixed horizontally. Aha, it is just like a guitar string. So this vibration stops at both ends. This wave does not travel to the right and to the left. So why don't we restrict ourselves to the standing wave generated on a vibrating string fixed. So if we consider the symmetry of two waves, they are propagating, identical wave propagating in opposite direction. They make a head-on collision. And in a classical point of view, the flow of energy or the flow of momentum is heading toward to the right and to the left if they are symmetric. That energy momentum transfer is just stationary. It does not move at all to the right, left, to the left, or to the right. We say it is a standing wave. Any standing wave is an even function, left-right symmetry. So this even function can always time as time goes by. So any time-dependent part can be replaced with a negative sign and added up. So then it becomes a completely even function. So that's the reason why the sum represent this, and this cosine omega t is an even function. And we have found that the separation of time-dependent piece and spatial contribution shows that it does not have a kx minus omega t structure. So this one has disappeared. Because of this wave does not propagate either to the right, neither to the right, nor to the left. So it is standing up and down, up and down, up and down. Instead, the amplitude becomes time dependent. If you take a picture at a certain time, the standing wave is something like this, and something like this, or this. This is not an even function in x, but we are interested in an even function in time. Okay. We require these boundary conditions. According to this, I can declare the sign k of 0 equals 0 always trivial. In any case, it is 0. It does not give any further information. However, if I substitute L, the right endpoint, then this function gives a strong constraint. Sign of something is 0 for any integer n pi. All right, so the wave number is completely determined by n pi divided by the length of the string. By the way, we have omega. And we have a strong constraint that the ratio of the angular frequency and wave number determines the speed of the wave, and the speed of wave is completely determined by the string tension and the density of the wire. Therefore, we know these conditions will give this standing wave. And every piece of this standing wave is a solution of the wave equation. If this is a wave equation for a certain n, satisfies 0, and if I add psi 1 plus psi 2, for example, if I substitute this, because this one becomes 0 and this one becomes 0, their linear combination is also 0. Aha! So, there are so many n's in here. Here we find is n equals a plus minus 1. They are redundant. If I substitute minus 1, then the negative sign comes out, can be included as an over factor. As a result, in addition, if I substitute n equals 0, it is nothing. Therefore, our solution is for n runs from 1 to arbitrary integer. And every solution satisfying a certain integer is represented by this, and any linear combination of them should be a solution. So this is the most general solution for this boundary value problem. And actually that is our, if you hear the vibration of string, the guitar string, sometimes it gives a very low frequency, but if you pick it up very strongly, suddenly, then it can vibrate more frequently. So higher frequency may appear. So, in general, the sound is very rich because of the wide spectrum of these frequencies. This is eventually developed to study the Fourier series expansion. It's very, very useful information. But most of them, most of mathematical objects develops from this physics by solving the physics problems. So perhaps you might think that I'm dealing with too much mathematics. No, it is physics, and it's not an application of mathematics. It's the origin of mathematics. Most of you have learned, you have studied, and will, except for a few mathematicians. Okay, for any physics major students or engineering students, you must study physics rather than mathematics. Mathematics doesn't tell you anything about the physical result and the origin of the equation. Only in physics you can learn why we have to solve this problem and how to solve this problem. Physics is so much important. Thank you for listening.